Hello, all. Welcome to this webinar on data science and nuclear engineering with Dr. Kathryn Huff. We will give in another 5 minutes for the audience to settle in, and then we'll start on full swing. Thank you for your patience. All right, let's begin. So, Pirater Mumbai is actually very excited to present Dr. Kathryn Huff for this exciting webinar on data science and nuclear engineering. I will introduce Dr. Huff, and then we can proceed with the webinar. So Dr. Kathryn Huff is an assistant professor in the Department of Nuclear, Plasma, and Radiological Engineering at the University of Illinois at Urbana-Champaign, where she leads the Advanced Reactors and Fuel Research Group. She is additionally a Blue Waters assistant professor with the National Center of Supercomputing Applications. She was previously a postdoctoral fellow in both the Nuclear Sciences and Security Consortium and at the Berkeley Institute of Data Science at the University of California, Berkeley. She received her PhD in nuclear engineering from the University of Wisconsin-Madison in 2013 and her undergraduate degree in physics from the University of Chicago. Her current research focuses on modeling and simulations of advanced nuclear reactors and fuel cycles. She is an active member of the American Nuclear Society, a past chair of the Fuel Cycle and Waste Management Division, and recipient of both the Young Member Excellence and Mary Jane Ostman Professional Women's Achievement Awards. A warm welcome to you, Dr. Huff, for presenting this webinar with us at this time. One more thing, Dr. Huff, we also have audiences from PyData Pune, PyData Ahmedabad, and PyData Gandhinagar joining us for this exciting webinar.
Well, I'm absolutely thrilled to be here. I hope you can hear me.
Yes, absolutely.
Excellent. So I have shared my screen on our Google Hangout, but all right, excellent. It seems to be appearing on YouTube now, so that's great. Oh wait, it went away. Ah, very good. Okay. All right, great. So generally speaking, I am absolutely thrilled to be here. I'll be giving this talk sort of with a focus on history and some background around how data science has evolved in the context of nuclear engineering. I hope you enjoy these slides. If you have any questions, I am vaguely watching the comments on YouTube, so I'll try to jump in if anyone has a specific question and I have a chance. I'll be watching those chats while I am talking. All right, so thank you so much, Sukanya, and everyone for having me. I will skip some of my introduction because you gave such a kind introduction to me already. The first thing that I'll just share is that I have worked on a large number of software applications and been in a large number of institutions that have contributed to my work, and those include the University of Chicago, Wisconsin, Berkeley, Illinois. I'm involved in the American Nuclear Society, and I've developed some software like Cyclus, a fuel cycle simulator, Python for nuclear engineering, Python for reactor kinetics, etc. Generally speaking, those things aren't really the things that matter in the context of today, however. A lot of the things around today are sort of how my other experiences, like the Berkeley Institute for Data Science, SciPy, software carpentry, etc., have contributed to my science. Some of you may have seen a few of these slides in previous talks, but I'll say a large amount of this is new. So bear with me, but all of this is for the Earth. So I'm a nuclear engineer because I care enormously about our planet. I generally would like to see it be a cleaner and safer space. And I think to do that, we need to do reproducible science, and especially reproducible nuclear engineering, because nuclear energy is going to be one of the most important features of a clean energy future. I know in India, there is an enormous amount of nuclear engineering research, and that research has a great deal of promise because of the technical prowess of Indian scientists and because of your natural resources, which will enable some very safe, very interesting advanced nuclear reactors. And I think that will empower the people of India someday to have large amounts of power that will fuel your world. So I'm very hopeful for nuclear engineering. Anyway, so this quote is from Richard Feynman in 1974. He was a physicist that worked on the Manhattan Project. That effort was ultimately about the nuclear bomb, but unfortunately, that on its own is extremely unethical and was a really sad period of our lives. But the physics that went on in that period really shaped the way that we do nuclear engineering today towards energy. And the people that were there were some of the top physicists in the world. One is Richard Feynman, who is quoted here, and two others in this photo are John von Neumann and Stanislaw Ulam. The three of them together are partially responsible for what is now known as the Monte Carlo algorithm. At the time, it was known as the Metropolis algorithm, And together they, in the 1940s, helped to produce one of the first generic algorithms that would then be run on the very first generic computer. And that algorithm was targeted at the problem at hand. And for them, the problem at hand was a physics problem. It is the multiplication of neutrons. The neutron transport equation describes the number of neutrons in a multiplying medium, like a bomb or a nuclear reactor. And it helps scientists understand how to control that reaction. In order to solve that equation, Stanislav Ulam, John von Neumann, and Richard Feynman, as well as many others, including Claude Shannon, Oppenheimer, Enrico Fermi, and many others contributed to algorithms that are now used ubiquitously today in data science, and specifically the Monte Carlo algorithm. If you've ever heard of MCMC, Monte Carlo was developed for nuclear engineering, but is now used for things like deciding which word comes next when you're texting your friends. I'm not seeing any comments in the YouTube, so I don't know, maybe they've been turned off or something. But if I see any, I probably will answer them. So if anyone has any questions, feel free. In any case, these three developed this Monte Carlo algorithm specifically to capture neutron transport physics, right? And that algorithm ended up being the very first program that was run on the very first supercomputer. This occurred in 1948 in April. John and his wife Clara von Neumann put this together, as well as Nick Metropolis and many others. So this was the first computerized Monte Carlo simulation, but also the first code ever written in a modern paradigm, that is a stored program concept. So very interesting, and an interesting bit of history that ties, Monte Carlo directly to nuclear engineering. So sort of a little known fact. And we still use it, but why? And why was the Monte Carlo algorithm invented for nuclear engineering? So to understand that, we have to back up a little bit and understand the nuclear fission reaction. So in this image, we have a white neutron striking a red and white radioactive isotope, or stable isotope nucleus in general. As the neutron strikes the nucleus, there on the left, it can be absorbed and cause an excited level of energy in that nucleus. When that excitement is too much for the nucleus, in certain situations, the nucleus will separate, and this is called fission. Fission is most likely in the kinds of large atoms that have quite a lot of neutrons. And so these are atoms like uranium-235, plutonium-239, uranium-233, etc. We would call these fissile atoms. And these atoms, once they have fissioned, so they've broken into two pieces, what they do is release some energy in the form of heat or gamma rays, and they also release more neutrons. The neutrons effectively boil off of the reaction. The neutrons then proceed to continue with a neutron chain reaction. That neutron chain reaction is the one that keeps a nuclear reactor going. We want to have exactly as many fissions in the first generation of fissions, that is caused by the first set of neutrons in the reactor, as in the next generation of fissions. So the fissions that are caused by the neutrons that were created in the first fission. Ideally, you want that to be constant so that your nuclear reactor runs super safe and flat. In a nuclear weapon, John von Neumann and them were ultimately looking for a much different kind of reaction. They were looking for a supercritical reaction. And that is what this image shows. The neutron generation, the fission generations increase over time, and you can see it's sort of exponential. And that is called a prompt supercritical reaction. We in nuclear engineering try to keep our reactions exactly critical and flat and stable. To understand this, we talk about the population of neutrons. This equation at the bottom is the neutron flux, and it depends on energy as well as direction, position, temperature. Temperature and energy are related, but in a sense, we must think about the energy of the neutron and the temperature of the isotope that it strikes, because both impact the flux. So this is a really complicated term, but it is the number of neutrons in the reactor. So this is like, I'm presenting this problem that is at the core of nuclear engineering. This problem is how many neutrons are in the reactor. If you break this out, it is a 7-dimensional equation. So we can ultimately think of this as one of the like higher dimensional physics that we are concerned about in the real world. To identify the flux, the number of neutrons in the reactor, we have to incorporate a large number of dimensions. So at its heart, nuclear engineering is very data focused. Something to add about this is that the likelihood of any certain reaction to occur in a nuclear reactor is associated with a cross section. So this is the probability density of the likelihood of a particular reaction happening if a certain particle is to strike that isotope. So a specific isotope may have a high probability of fission, and that would be represented by a large cross section. An isotope that has a very low probability of fission when struck by a neutron would have a very small neutron cross section. Yes, Robin Patel, it is exactly the same as used to produce nuclear energy. I do not study nuclear weapons. I am describing a problem that is true in both nuclear energy and nuclear weapons. So what happens when this fission happens to a free neutron is your question. So the free neutrons, sometimes they escape. So I see your question here, and the idea is, so all right, a couple neutrons may cause other fissions, but some neutrons will escape the system. So to answer your question about free neutrons, we have some neutrons contributing to future fissions. Some get absorbed in other isotopes that do not fission. They simply change the nature of that isotope. This is called transmutation. And some neutrons escape the system. The majority of neutrons will be absorbed in the system in a typical nuclear reactor. Great question. All right, onward. So what happens to the two halves of the isotope? Well, these are called fission products. So this diagram indicates the distribution of fission products over the full range of isotopes that can be created in a nuclear fission. And you can see here that there are two humps. What this represents is the fact that the fission tends to result in one half that is not a half size of the isotope. It is not a half of the uranium atom. It is instead about the size of 1/3 of the uranium atom. And the other isotope is about a size of 2/3 of the uranium atom. So it turns out we have two humps, and fission typically results in a 1/3 piece and a 2/3 piece of the uranium isotope. That yield is of great importance, and indeed it covers the full range of possible isotopes that we are aware of. This diagram here is at the core of nuclear data in nuclear engineering. This is the chart of the nuclides, and what you see is number of neutrons, number of protons plotted here, and the isotopes that we're aware of each make up a single tiny little block. The stability of those isotopes is plotted in the color scheme, and you can see that black isotopes straight in the middle of that graph are quite stable. The ones on the outside of having too many neutrons or too many protons are unstable, but we're talking about thousands of isotopes that we're concerned with in nuclear engineering, and almost all of them are created inside a nuclear reactor. So why am I telling you all this about the kinds of things that happen inside a nuclear reactor? Well, the reality is this has always been a big data problem. If you're interested in a dozen nuclear reactions and you're interested in thousands of isotopes at an extraordinarily large range of neutron energies and a couple hundred degrees of isotopic temperatures, now you're dealing with a system with that in order to simulate it relies on an enormous volume of data. That enormous volume of data is at the core of this problem. I see the question, is this called a Serre plot? So yes, I think the Emilio Segre was responsible for one of the first demonstrations of this. We tend to call it the chart of the nuclides because you can plot other things in a Segre sort of way. Great question, Archie. Okay, so these are all the isotopes we're concerned with. The energies, so those probabilities vary dramatically over energy, all right? And so if we're interested in neutrons that might happen inside a nuclear reactor, we're interested in a very large range of energies. And the probability of a single reaction, for example, fission, is not a linear function over that energy. You can see there are some profound resonances in this probability distribution over energy. And because of this kind of complex data problem, it is not only a large data problem to generate simulations in nuclear engineering, but also a complex data problem. You have data that is like quite strange, like this plot, and that is at the core of our simulations. All right. So there's a whole bunch of different things that identify why these probabilities happen. And so there's a great deal of physics at its heart. Ultimately, nuclear radioisotopes hold their nuclei together with 5 nuclear forces, sort of 5 nuclear concepts. The volume of the isotope matters, the surface area of the isotope's nucleus matters, the Coulomb force that sends protons away from each other matters. The asymmetry of the nucleus can contribute to its stability or instability, and similarly, being able to create pairs of neutrons and protons can also contribute to stability. And this nuclear structure is all a part of how we evaluate these nuclear data sets. Getting these nuclear data sets together has been an enormous effort over the course of the last many, many decades. Hundreds of PhD theses and extremely large experiments have been dedicated to this activity. And each of those resonances that we saw in the previous experiment is evaluated in the context of the nuclear theory behind it. So this should give you a taste of what kind of complexity we're dealing with in nuclear engineering. And we get those probabilities, that sigma that I showed you earlier, at the core of our sort of question in simulation. We get that from a combination of both nuclear structure theory and the experiments that we conduct. The experiments can be very complex. This is a diagram of an experiment that's similar to one called the dance detector at Los Alamos National Laboratory. By striking a sample at the center of this detector with neutrons, we can evaluate with a large array of photomultiplier tubes, we can evaluate the likelihood that that isotope has had a certain reaction or not. And that is where we get these cross sections. This is what that experiment actually looks like. So those of you who are experimentalists will not be surprised to know that that it's a bit of a mess. But this is the dance detector at Los Alamos that's responsible for a large amount of that cross section data. All right, what does it mean? So we're going to talk about data science and nuclear engineering, not just like what data is in nuclear energy. I'll say, so for my purposes, nuclear data is for simulation. Sorry, this is coming off the screen a bit. But at the bottom here, you'll see there is a nuclear reactor core that I have modeled, that my student Andrei Ryklevsky has modeled. This is the molten salt breeder reactor core from the top. And we have conducted a Monte Carlo simulation of neutron transport in this reactor to ask questions around its design. This reactor has a great deal of breeding around the edges and a lot of fissions in the center of the reactor. It is a really interesting reactor, and we're interested in it in part because of its ability to use thorium, which you may know is a really available resource in India, but also, you know, in a number of other places. But just relevant to you guys, you should know that this reactor actually might be a very good option for all of you someday. And it's very inherently safe. We use the Monte Carlo algorithm and all of that nuclear data to run these simulations, which we run on Blue Waters. But I also have a lot of other simulation types that I run. One is a type of simulation called the nuclear fuel cycle simulator simulation. We do this with agent-based modeling in the Cyclist framework. I'll talk a little bit about the Cyclist framework if we have time. We do reactor kinetics with a tool called PYRK in my group, P-Y-R-K. This is a Python tool for evaluating the transients in molten salt reactors. We do large-scale finite element models using all of that data. We rely frequently on a framework called MOOSE, developed at Idaho National Laboratory, and I am a happy contributor to a toolkit called PINE, the Python for Nuclear Engineering Toolkit. This toolkit is one of the first forays into collecting a lot of the nuclear data that we have into a single Python API. There are a lot of simulations that people do in nuclear engineering, however. In addition to Monte Carlo, there's a fleet of deterministic methods rather than the stochastic nature of Monte Carlo. There are deterministic strategies for solving the neutron transport equation. Sometimes mixing deterministic methods and Monte Carlo will accelerate the speed of Monte Carlo. We'll talk a little bit about how machine learning can contribute to that experience. And generally speaking, scientific computing comes in a lot. I would describe scientific computing as these like lattice codes, ray tracing algorithms, acceleration schemes, agile methods, etc. All of this, however, relies on what I would call data science generally. So in order to do the data processing, we need to do a lot to that cross-section data. It involves energy discretization, including multi-group discretization, point-wise discretization, etc. We use tools like angular quadratures to do clever integrations for geometric handling of those large data sets. We typically have to use our physics intuition to integrate over some of those complicated resonances that you saw in the cross-section data, etc. And so this kind of, quote, data science, which you might call sort of data processing, has been happening in nuclear engineering since the dawn of the computer age. And so a lot of the data processing that we do day to day in all science has been contributed to by the methods that were developed for nuclear data processing specifically. So it's something we can be very proud of in nuclear engineering. All right, but how do we know it's right? So we do a lot of benchmark experiments in nuclear engineering. Early on, these benchmark experiments were sort of dangerous. In this image, Louis Slotin is experimenting with a device that goes critical if you put two halves of the sphere together. And this would be a very dangerous situation. So you want to keep those two halves apart. But the approach to criticality, as those two halves approach one another, we get more and more of a nuclear chain reaction. As that nuclear chain reaction grows, as he's inching those two halves of the sphere together, he can count with a detector on the side how that approach is happening and understand a lot more about reaction rates in nuclear reactors. Now, unfortunately, Louis Slotin died because of this device. You can see he's not being particularly careful to keep these two halves apart. He's using a screwdriver. And this is not a particularly safe approach. He's not the only person that was killed by this device also. It is called the Demon Core. Generally speaking, without going into the great detail, we use these benchmarks to ask the question, have we evaluated these data sets correctly? Have we processed them correctly? Unfortunately, there is a lot of room for interpretation, and because the data sets are so complex, different evaluated data set releases from different nations in particular. So the United States has its own evaluated nuclear data set. Japan has one, etc. So different nations and different nuclear organizations have different evaluated nuclear data sets, and it turns out they have self-correcting internal errors. So there actually is a really complicated data problem inside the reliability of that data. I won't go into great detail about this, but if you are interested, I would strongly recommend looking up some of the papers around cross-section and evaluation in nuclear engineering. All right, what are specific applications in nuclear engineering where we can apply AI and ML? I'm going to ask you just to be a little bit patient. I'm getting to those slides really shortly. Thank you very much, Anju. One thing to say is there are a lot of skills that you need to make sure that like my graduate students, for example, tend to require, oh, I guess this slide is cut off a little bit. My graduate students tend to require a great deal of skills, and if you are interested in doing sort of data science and scientific computing in nuclear engineering, I would say that you probably want to grab a few of these skills that I'm listing here on this spreadsheet. All right, next. So I'd like to talk a little bit about Cyclist, which is a nuclear fuel cycle simulation framework, but given that there is a great deal of interest in terms of AI and machine learning, I will just say that inside Cyclist, we are developing reduced order models for facility representation. I will introduce what we do in Cyclist, and then I will comment on what we're doing for the modules in Cyclist. Cyclist itself is a fuel cycle simulator for asking questions around how groups of facilities work together. So we use agent-based systems analysis, which is certainly not machine learning or AI, but can incorporate machine learning and AI inside the agents. All right, and so in my simulations, we have hundreds of discrete facilities. Mines, where you mine uranium, mills, where you change its composition, conversion, fabrication, transmutation in the reactor, and various reprocessing and recycling schemes, as well as storage. These systems are very complex, nationwide, international, and tend to involve hundreds of facilities, hundreds of years, and very complex physics. In order to simulate something so complex with so many moving pieces, agent-based systems analysis allows us to create different agents that are very detailed but can interact with one another. So a reactor agent, for example, can be a very complex agent, but we want to run reactor simulations very quickly. And so some machine learning can be used to help those agents figure out how to act with one another. I'll just say, like, the way that this works in the simulation is that there's a source facility that might produce some material. Many materials might come out of a single facility. There's a sink facility that might request material. Many materials might end up in a sink facility. This is something like a repository. And it might do both. So like a reactor, for example, might accept some material and send some material. But then how does it make its decisions? All of that is in this black box of the facility agent. And agent-based systems analysis lends itself really well to reduced order models produced by artificial neural networks. So one direction that we have been going in this work has been to reduce the computational time that we spend calculating the behavior inside reactors, and instead approximate the behavior inside reactors based on trained neural networks. So this is a paper that will come out. It was produced by my graduate student in Monte. And ultimately, what I will tell you about this is that if you are interested in a complex physical process, and you want to know how that physical process, for example, enrichment of nuclear fuel, if you're interested in how that physical process is impacting the broader system of the nuclear fuel cycle nationwide or over hundreds of years, it's important to embed that process into a simulation like this. But because of the many facilities that you would have to simulate, the many thousands of time steps that you would have to simulate, that high fidelity model may take too long and the computational time is a burden. So replacing agents with reduced order models created by artificial neural networks is a direction that we go in nuclear engineering. Another thing to think about is that there's like a really long history of what one might broadly call data science in nuclear engineering, but machine learning specifically has already been incorporated in nuclear engineering in a lot of ways. Demonstrated success has included radioisotope identification from gamma spectra, which I'll go into in some detail as this is work that I am conducting with my graduate students here at the University of Illinois. There's also work around radioisotope localization, so finding where a radioactive source is in the environment, like if you've lost one, for example. That work has been demonstrated recently by Mattingly Myers-Smith. Mechanical failure detection. So in nuclear reactors, we have a basically zero tolerance policy for failure. And so if any tiny cracks develop in what's called the pressure vessel of the nuclear reactor, we absolutely need that mechanical failure to be detected well before it expands. So mechanical failure detection in the pressure vessel has been demonstrated. It has been demonstrated that you can use machine learning, specifically artificial neural networks, to train on information around the mechanical behavior of those materials and identify situations, predict situations in which small cracks are being generated inside a pressure vessel. So this is work from Purdue University, Chen, Jahan, Shangxi, et al. Additionally, in the context of post-Fukushima environmental analysis, the radioactive material dispersion that happened shortly after the Fukushima event has been modeled using machine learning and AI algorithms by the University of Tokyo. Some sort of active areas of open research that other folks are working on, and I'm actually working on some of these, that don't have demonstrated success with machine learning, but there's an open question as to like how well we could incorporate machine learning into these areas, are optimized reactor fuel arrangement. So when we refuel a nuclear reactor, we need to shuffle the fuel around and put fresh fuel in some places and spent fuel in others. Optimizing that arrangement of nuclear fuel is a great place to put some machine learning. Previously, we've used kind of old school methods for optimization, like simulated annealing and whatnot. I think some advanced trained neural networks and sort of deep learning could be used with the large fleet of data that we already have about nuclear fuel performance in our power industry today. So if we can get some of that data to use as training, perhaps we can optimize some of the fuel arrangements in future reactors. Additionally, simulating data for fuel arrangement optimization can provide a training set, whereas the test set obviously would have to be some of the real data from the real world. Accelerated Monte Carlo. So I made a comment about this earlier, that we have various ways inside nuclear engineering that we combine our deterministic solutions to the neutron transport equation to accelerate the Monte Carlo neutron transport approach. The way that this works is a hybrid method where you solve deterministically the problem, but very badly, and then you run a detailed Monte Carlo simulation, but only using the importance map. Now the question here is, could you accelerate Monte Carlo with a learning algorithm? And to what extent can we incorporate AI to bootstrap Monte Carlo on top of itself, for example? This has been demonstrated in the context of quantum physics in the past, and I have a project right now attempting to apply this to our neutron transport simulators. Additionally, nuclear fuel cycle safeguards are an area where AI and machine learning can be applied. Ultimately, as we produce nuclear fuel for nuclear power, there is always a concern that at some stages of this nuclear fuel cycle, material might be diverted by a nefarious actor, a terrorist, an unscrupulous nation state. That material needs to be safeguarded by the International Atomic Energy Agency. And the ability to safeguard that material can be informed by learning algorithms around where and how to place detectors and how to assess the uncertainty and impact of uncertainty of those detectors to reduce false positive rates and to increase true positive rates for detection of diversion in nuclear fuel cycle facilities. I see there's a question around using thorium instead of uranium from Sohel. I actually I did mention this earlier in the talk. Using thorium is a great choice if you have a large thorium deposit, especially in India. I would say this is something to be considered as you have very large resources in thorium. There's nothing inherently different between a thorium reactor and a uranium reactor because uranium-233 is the fissile material. In a thorium breeder reactor, the notion that it's more proliferation resistant is false. So I think this is something that people need to be aware of. Plutonium isn't produced by a thorium type reactor, at least very, very tiny amounts, but it is produced in a uranium type reactor. The real difference here is that plutonium and Pu-239 and uranium-233 are equally weapons usable. And so people forget that in a thorium reactor, we are producing a weapons usable material that is exactly as helpful to make a weapon as plutonium. And so they are equally proliferation causing. And so a lot of claims around thorium being this magic bullet are sort of false and drummed up. Nuclear power is very safe and generally speaking, not proliferation resistant. And as long as you can safeguard the facilities, you're okay. So thank you for that question, Sohel. Next. So I told you I would tell you a little bit about one project that we're doing in radioisotope identification. So my graduate student, Mark Kamuda, who will be getting his PhD very soon, was interested in the following question. Imagine you find a box, and in that box, there is some source of radiation. It seems to be a mixture of materials. The things that you would want to know about this box are, is this dangerous? What isotopes are in this? Where did the box come from? Who produced it? If it's a mixture of isotopes that are somewhat radioactive, is it a fissile material? Is this a weapons usable material? And should you be concerned? But typically our only tool in this endeavor are sodium iodide type handheld detectors. In an urban environment, if there's an urban source available, we want to interdict that material with a handheld device where we we hold that detector towards the source and we count the photons that come off of that radioactive material. This unknown radioactive material might be coming through a border portal. So as people move from one nation to another, they typically go through a radioactive portal. It may be in a shipping container facility that inspects shipping containers, or it may be our emergency response first responders in an emergency situation where a source has been placed in a public space. And so one problem with these sodium iodide detectors is that they are small and helpful, but not very accurate in their gamma spectroscopy. And so what we learn from doing this detection on this box is we get a single photon spectrum. We see the energies of the photons that come off of this reaction. It would be helpful if, in addition to these gamma spectra, we were able to just automatically identify the mixture of isotopes that created that spectrum. So here's a paper, a comparison of machine learning methods for automated gamma ray spectroscopy. This is my student, Mark Huda, another student here at the University of Illinois, Jifu Zhao, and of course myself. So this automated identification of gamma ray spectra is for non-proliferation applications. Historically, identification of such spectra has been done by humans. Like image analysis, it therefore is very promising for the application of machine learning. Much like image analysis, humans are very good at it, and computers need to use some machine learning in order to be good at it. So what basically happens is you look at a gamma ray spectrum, which I'll give you an example. I'll show you as much as I can here. Here, I'll just open this and you should see it a little more clearly. So this image here, this blue spectrum is a gamma ray spectrum. Well, actually, let me find you. So this is the structure of the neural network structure for the input spectrum. And this is the input spectrum from cobalt-60. I'll show you, sorry, I'm flipping around a little in this paper. Let's back up a little. So if all we get is a gamma ray spectrum, we can sort of identify some photo peaks from this gamma ray spectrum. But we want to use an automated algorithm to extract information about that spectrum, compare it to what we know about the gamma rays that are emitted from isotopes in isotopes of interest, and then we want to output information about what isotopes exist in this scenario. So we take a typical artificial neural network with an input layer A, some hidden layer B, and an output layer C. The input layer is basically our gamma spectrum. The output layer is effectively like what we want to know. And the thing that we want to know is what isotopes made up this mixture. And so using hidden layers and a deep learning algorithm, we have been able to so we've tested a number of different dense layer sizes and dropout rates, as well as kernel sizes. And we compared a bagged, fully connected neural network with a convolutional neural network. And we compared what the predicted mixture of isotopes was to the reality. And it turns out they were both pretty well performing for sort of ordinary spectra that are simulated using a training, like to create the training data set. When the spectrum, total counts in the spectrum is pretty high, it does really well. When we have a situation like in figure 6, where the training data set is sampled from a measured spectrum, the training data set is full of noise and gain drift and calibration issues. And it turns out that our ordinary convolutional neural network fails while a bagged, fully connected neural network succeeds. And so some things that we've learned here that we're applying to new research is that we can take certain neural networks, and if we train them on measured spectra, so like real life spectra, they might not do as well as if we train them on intentionally augmented gamma spectra through simulation. So if we augment the gamma spectra to incorporate things like calibration of that detector, the gain drift in the detector, temperature dependence around sort of the detector's performance, or detector efficiency, et cetera, then we can get a much better result. What we've sort of seen is that we've been able to predict very well what isotopes are in a sample, and this article is available online. But I'll tell you, we have a whole bunch of other things going on, so I'll show you another example of this application. So one thing that we've tried to do is develop a radioisotope identification algorithm that includes, so after that work, I told you sort of there's this problem where different detector behaviors might result in a bad behavior of the neural network. Well, now we've incorporated shielding configuration, radiation background, so the natural radiation in our environment, and a number of detector calibrations. Historically, we thought that maybe dense neural networks might be helpful, but we wanted to check because ultimately we thought convolutional neural networks would do better as they assume nearby channels are related to one another, which actually in the context of nuclear engineering and gamma spectra, this is also true. So nearby channels are related, so CNNs should operate better than DNNs. So this was the theory, and indeed we showed it. So what we did is we took gamma ray spectrum templates. We used a simulation tool called GADRAS. We simulated spectra from 29 isotopes with lots of different calibration scenarios, like a badly calibrated detector, et cetera. And then we assumed that instead of just a box with a source in it, we said, all right, what if someone has shielded that box to hide the radiation? And so we assumed a couple of different amounts of shielding thicknesses, and we used those templates to train a classification dense neural network. We did some principal component analysis and fed that into a dense neural network, and then we compared all of that to convolutional neural networks. I'll show you sort of our weighted results were compared for simulated spectra. The F1 score is the accuracy determination, so 1 is good, 0 is bad. And generally speaking, with no calibration shift, but some lead shielding, we see that we have unshielded CNN trained really well, shielded CNN, shielded CNN trained really well, unshielded CNN was incapable of picking up isotopes with some shielding, and so you can see how training incorporating shielding performs much better on the real scenario. So all three that performed well incorporated shielding into their training, and CNNs performed much better than DNNs. This bears itself out in all following plots in this poster, which in the slides you can see online. This poster is available to you. I'll say one more thing. So as we incorporate background from natural radiation background, we start to see that the impact of shielding is not as important as background. And so one of the recommendations that we get from this is that if you're going to include something in your training set, the most important thing is to incorporate background. So CNN's performance was the most promising, which is consistent with our paper that we showed you before. And our future work is to kind of investigate some different output structures and understand a little bit better unsupervised feature extraction. So I hope this was a good deep dive into one application of advanced machine learning and neural networks in nuclear engineering. I have a question here. I have two. So one is about many body systems in nuclear physics. That's great. I appreciate this question, 100 Deep, but this is actually well outside of what I'm talking about today. So I'm gonna skip that question. I see a question from Devish Kumar, which is asking about what is super MC and hybrid MC. And I sort of touched on this a little bit. There's a combination of deterministic algorithms and stochastic algorithms that we call hybrid Monte Carlo. So hybrid Monte Carlo uses things like the diffusion solution, the deterministic diffusion solutions and quadrature sets to accelerate the speed of ordinary Monte Carlo neutron transport. So those algorithms actually are very similar to the kind of generic super MC and hybrid MC that you see in the real world. I hope that answers your question. And then Aniruddha has asked, is this algorithm capable of identifying a mixture of radioisotope radioactive elements. Yes, that is exactly what I'm saying. This algorithm does exactly that. It takes a set of photopeaks and it evaluates those photopeaks. We've trained it on a set of simulated spectra. It takes those photopeaks and it says, like, what's the mixing coefficient of each of the isotopes in the spectrum? And it seems to succeed pretty well in certain scenarios. In his thesis, my student Mark Kamuda, who is one of the authors of this work and the primary author, he has demonstrated some really flexible training for that. All right. So let me continue with the talk and then I'll answer further questions in a bit. So I hope that was useful. I'll just point out one final thing. In nuclear engineering, unlike a lot of other fields, there's a great deal of export control where there are sort of nuclear codes and nuclear software we can't share directly with other people because there's information in that software that can be used to build a nuclear weapon. Machine learning, because it obfuscates, it confuses the user a bit by putting everything in a black box. Machine learning may be helpful in allowing us to share nuclear reactor physics capabilities without sharing nuclear weapons physics capabilities. This is just an idea that I have, but I think that there is an opportunity for us to improve peaceful uses of nuclear energy and without the concern for non-peaceful uses of nuclear energy. And I think there is a possibility that machine learning and especially neural networks could be used to contribute to that because they tend to obfuscate the physics. So there you go. So that I think I wanted to just point out. And here's some links here. There is basically, this is the link at which you can find these slides. So if you had any specific questions or you wanted to look at those papers more closely, you can go ahead to that link. And in the meantime, I'm happy to answer y'all's questions. So thank you for listening. Ankita Prakash, I see your question. What skills are more appropriate for a career in data science and nuclear engineering? That of a data science or of a nuclear engineer? I believe that nuclear engineering is more important if you are going to be a nuclear engineer that does data science. Ultimately, all of our physics is at the core of developing, training, and interpreting any results that you would get out of any kind of data science, any kind of neural network that you've produced, any kind of training that you do, needs to be informed by reality. Otherwise, you're just producing black boxes that you don't understand. Trained neural networks are useful, but only to someone who understands what went into the training, what went into the testing, and what answers you're asking. Because without an idea of the physics, you will not be able to identify sources of bias or sources of error that you accidentally introduced in training. The physics is the most important. If you're going to use machine learning in any field, I would say the field is the most important, and the machine learning really is a tool. So unless you're developing machine learning algorithms like at their core for general use, then it is the science that is the most important, because a misuse of machine learning and AI is much more likely if you do not have the science background. So I hope that answers your question. So you asked this question, Mayank Mishra. You want to know more about the agent. How are they using neural networks? So here's an example. If you have, in a nuclear fuel cycle simulator, it is important and interesting to know what isotopes are in the spent fuel. The number of variables that impact this are extremely large. There's like a lot of variables that impact this question, and over the course of a reactor's lifetime, it may produce many different types of spent fuel based on the fresh fuel that was loaded in, the time that it ran, the times that it shut down, the way that it operated, what power it operated at, etc. If you're doing that for hundreds of reactors over hundreds of years, you don't want to recalculate that isotopic composition every 18 months for every reactor for every year, right? It's like, that would be problematic. So what you want to do is create a data set that you can train a neural network, and that neural network will operate much faster than our transmutation depletion codes. So you can replace a really high fidelity software that calculates that question, that like gives you that answer inside the reactor, and create a reduced order model with a neural network. So I have a student who has recently graduated. His name is Jin Wanbei. You can find some of his code. on GitHub, where we're working on this. We're submitting a paper very soon about this topic. But in Cyclist, we have together used a database of spent fuel compositions to train our reactor model. And now our nuclear fuel cycle simulations can be higher fidelity and faster because they've learned on the full set of spent fuel composition. So it can conduct a transmutation calculation without thinking about the physics. All it knows is the relationship between past operational states and fresh fuel and past corresponding spent fuel compositions. I hope that answers your question. It's a little confusing, but Mayank, it's a good question, so thank you for it. Now, Shiket, you ask, how close are we to a new type of fuel for better rockets? So I don't do rockets. I do nuclear reactors, but nuclear reactor fuel, there's a lot of better types of fuel. Here in the United States, molten salt reactors are of great interest. So nuclear fuel for molten salt reactors is a liquid type fuel. And we've produced it here in the United States. Here at Illinois, we have an experiment where we're looking at some of the chemical properties of liquid salts just for this purpose. There are also accident-tolerant fuels that are solids that are being implemented for production in the United States reactors, power reactors, in the next few years. 100 deep, how do you generate accelerated Monte Carlo simulation? Restricted Boltzmann machines, delete deep belief networks. It's funny you say restricted Boltzmann machines because that was my first attempt. So there is this demonstration in quantum physics that restricted Boltzmann machines work for bootstrapping Monte Carlo simulations of particle physics. And so that was our first attempt. So I had an undergraduate work on that, using restricted Boltzmann machines to accelerate Monte Carlo with results from early non-converged solutions. Unfortunately, what we found was restricted Boltzmann machines may be a little bit too weak. They don't seem to learn. They seem to incorporate an enormous amount of bias from the initial source calculation. I won't go into the great details, but basically we have a source iteration problem in our Monte Carlo neutron transport codes that it has to converge or else you start to diverge to a wrong answer. And so restricted Boltzmann machines are very sensitive to that bias. We're trying some new things, but we'll see how it goes. Mayank Mishra, is it using a DNN or a CNN? You mean the agent in our previous conversation. That agent was using a Keras sequential model with dense neural network, with a handful of dense layers. So it's technically a deep learning algorithm. We were using k-folds cross-validation. I hope that answers your question. Basically, the answer is it's a dense neural network with k-folds cross-validation through the Keras library using scikit-learn. Yeah, so I think it's probably time to let you guys be free. It's nice meeting you all. I don't know how to turn off my screen sharing, but there we go. Hello.
Great. Thank you, Kathy, for this wonderful webinar. Any further questions? No, so I think we are good. Thank you so much for this wonderful presentation, and thank you all for joining this webinar. I think we can close this.
Thank you for having me. It was wonderful. Bye.
It was a pleasure. Bye.